Let's get some practice of calculating probability from a contingency table, or our two-way table. So here what we have is some data in terms of parents and whether one or both or none of the parents smoke, and then whether the student smokes. So this we're trying to connect, is there any relationship between student smoking habits and their parents? So in here, we'll kind of touch on all of the probability that we talked about a little bit from the previous module, and then throwing in this new conditional probability and how that shows up in the table. So this first question, what we're looking for is just the probability that a student smokes. So this is the case of just looking for the probability of a single characteristic, meaning we're really looking at just this group here. So we really just want to see how many people fit this group of students that smoke. And when we look at a single characteristic, your denominator is going to be out of everyone. We're basically saying out of everyone we surveyed, what's the probability that the student smokes? So what we can take is the total number of students that smoke, which is 1,004, out of our total sample size, which is 5,375. And that'll be a 0.1868. For the next one, we're looking for the probability that no parents smoke. Again, we're just looking at a single category. So with this, these are both marginal probabilities. Now we're using the values coming from the margins because we're just looking for the probability of a single characteristic. So with this, we want the total of none of the parents smoke, which is the 1,356, out of our total group, which is the 5,375. And that's going to be a 0.2523. With the probability that at least one parent smokes. So with this, and the wording of at least is wording that comes through when we're looking for more than or equal to. So to say at least one parent smokes kind of fits two categories. You can either have one parent that smokes or two parents that smokes. So both of those fit this category. And we could write this as probability of like one parent or two parents smoke. And this is where our addition rule comes in. We would want to take the probability of one parent smoking plus the probability of two parents smoking. So with this, the probability that one parent smokes would be the 2,239 out of the 5,375, and then add that with the probability that both parents smoke, 1,780 out of 5,375. And notice in this case, when we're using this addition rule for when OR comes through, these are disjoint events. And they're disjoint because they don't overlap. Since they're both columns in the table, there won't be any overlap, so we don't need to worry about taking away the intersection of the two events. So this should come out to be a 0.7477. With the next question, probability that the student smokes and one parent smokes. So when we're working with and here, this is the case where we're looking for two characteristics at once. We want them to fit kind of the two scenarios of we have the student smokes and we have that one parent smokes. And what we're really interested in is the intersection of the two. We want to bring through the probability of being one of those 416 students or people that have one parent that smokes and the student smokes. So this is where we use the intersection of the graph. So we take that 416 that have both characteristics out of the 5,375. And that's going to be a 0.0774. Then for the next one, we have the probability that the student smokes. So we know we're in this category, and at the same time that no parents smoke. So now the intersection that we're looking at are these 188 people where the student smokes and none of the parents smoke. So we want to take that 188 out of 5,375, which would be a 0.0350. With this next one, we want to have the probability that the student smokes. So we know we're going to be in this group. And at the same time, at least one of the parents smoke. So the groups we want to bring through here are these 400 or these 416. So it's going to it looks like an and scenario, but or is coming through from how we saw it in part C, this probability of at least one parent smokes. So to fit this category, it'd be that the student smokes and one parent smokes, or the student smokes and two parents smoke. So we're going to be adding together that 400 out of 5,375 and adding that with the 416 out of 5,375. And that should come out to be a 0.1518. All right, what is the probability that a student who smokes has no parents that smoke? So the wording here, and what you often want to look for is where it asks for the probability that, and what they're describing is who we're looking at. And they're saying we're only looking at students who smoke. So what that means in this case is this is our given event. They're saying we already know the student smokes, so then what's the probability that they have no parents that smoke? So this is going to be a conditional probability, and it's looking for the probability that no parents smoke given the student smokes. So in the numerator, we want the number of students that have no parents that smoke, but intersecting with the students that do smoke. So what we're looking at here is we know we're in this category of students that smoke, which means our sample size becomes this 1,004. We're looking out of these 1,004 students that smoke, and what's the probability that no parents smoke? So for our fraction, we're going to take that 188 out of 1,004, which will be a 0.1873. For this next case, what's the probability that if two parents smoke, their child will smoke? So with this one, they're saying what's the probability that if, and if is another word that comes through just like given, where it's telling us what we know already. So what we're being given is that we know the two parents smoke, and we want to find what's the probability that their child smokes as well. So probability that student smokes given two parents smoke. So with this case, in terms of our table, the category that we know that we're in is we know two parents smoke. So in terms of our new sample size, we only want to look up out of these 1,780. And now what we want to do is see what's the probability that student smokes out of this group. So for our fraction, we'll have 400 out of 1,780. And that's gonna be a 0.2247. For this next one, what we're gonna do is try to prove independence. So to do this, what we'll do is just choose a conditional probability. Since we've already calculated a few, we could just use what we know already. Let's use our results from part H. So we know that the probability that a student smokes given two parents smoke is 0.2247. Now, if we have independence, What that would mean is that it shouldn't matter what our given event is. If I look at probability a student smokes, it should be unaffected by any given event. Meaning, if we have independence, if I calculate the probability of a student smoking, it should also be 0.2247 if they're independent of each other, essentially eliminating the need for any given events. So, we calculated this in part A, and that was the 1004 out of 5,375. And what we can see is that came out to a different number of 0.1868. So those two values are not the same as each other. And what that's proving is that this given event changed the probabilities. And that means these two events are linked to each other and not independent. It means the probabilities change based on given values. So in this case, it is not independent because those probabilities differ from each other.